Hello, ladies and gentlemen. Welcome back. Chapter 8.1. We're going to learn about the binomial distribution, and this starts on page 513 in your book. But before we get into that, let me pull this in and let's take a look really quick at the calendar. So again, this is a very quick chapter. We're only going to spend 3 days on it. We're going to spend a day and a half on chapter 8.1 and a day and a half on chapter 8.2. And our next scheduled test is going to be for February 8th. All right, now, right above this video, there are some PDFs of the examples that I'm going to go through. Okay, if you want to print those, pause the video now and go print those so that you can write on those examples as I go over them. Also, underneath here, ladies and gentlemen, are the videos on the College Board website. I highly recommend watching them. We do have one against all odds videos in this chapter. It's right here. Please watch that. Take Cornell notes. Underneath, remember, there's video questions. Go ahead and answer those questions. There will be, I'm not done yet, and I got to take that D out of there. The video is not ready yet, but there will be a second part to this video. It will be probably quite a bit shorter than this first one. And then here's our book. And then again, here's the assignment for chapter 8.1. There are actually a couple other problems that are chapter 8.1 that are not on this page. You will find them on chapter 8.2 when we get to it. All right, and don't forget to submit your work as soon as you get things done. All right, let's get rolling here, ladies and gentlemen. So first of all, a binomial distribution, okay? It has to meet 4 conditions, ladies and gentlemen. Okay, binomial should be obvious. You know that bi means 2. So, number 1, the observation must fall into one of just 2 categories, which for our convenience we will call success and failure. Now, just warning, success doesn't always mean it has to be a good thing. Okay, success is the question that is being asked about. So, remember, it doesn't have to be a good thing to be successful, okay? Number 2, it has to be a fixed number of observations. Okay, we have to know exactly how many that is. That'll be key. That part of this will change when we get to 8.2, which is on the geometric distribution. Number 3, the observations are independent, okay? So that is, knowing the result of one observation tells you nothing about the other observations. 4, the probability of success, call it P, is the same for each observation. Okay, so that means it will never, ever change. And again, you will find these on page 513. All right, binomial distribution found on page 514. The distribution of the count X of successes in the binomial setting is the binomial distribution with parameter N and P. The parameter N is the number of observations. P is the probability of success on any one observation. The probability values of X are the whole numbers of 0 to N. As an abbreviation, we say, okay, so look at that abbreviation, ladies and gentlemen. B for binomial, parentheses, lowercase n for the number of observations, and P is the probability of success on that observation. Now, I do want to point out, and we saw this earlier that in the school year, the normal distribution with mean mu and standard deviation. Okay, sometimes, depending upon the situation, a normal distribution can be substituted using the z-score and the normal curve for a binomial situation. Okay, we will run across some of those, and I'm going to point those out as when we get to them. Okay, so in certain situations, the normal distribution can substitute for a binomial distribution. Okay, but we aren't going to see any of those today. All right, now here's our first example. 60% of all watches sold by large discount stores have a digital display, and 40% have an analog display. The type of watch purchased by each of the next 6 customers will be noted. What is the probability that exactly 2 watches are digital? Okay, so exactly 2 watches are digital? Well, ladies and gentlemen, first of all, we have to check our conditions. And yes, if you run across this on a free response question on the AP test, and it's binomial, you have to, this is part of the process, you have to go through those 4 conditions to make sure they're met. Okay, so today I'm going to do it like, for this problem, I'm going to do it like this. So the first condition, again, is success, okay, or failure. Now, we're going to call success buying a digital watch, and the failure will be buying the analog watch. Now, I'm assuming you all know the difference between digital and analog. If you don't, go look it up. All right. Number 2, the second condition. Okay, the second condition is fixed number of trials. Well, it says there are 6 customers. It is fixed. Okay, the third condition is independence. Well, to be independent here, obviously, the customers do not influence each other's purchase, right? Okay, the customers do not influence each other. All right. The fourth condition is the probability of success remains the same, which also in turn means the probability of failure remains the same. So in this situation, ladies and gentlemen, the probability of success is always equal to 60%, okay? 60%. And remember, we never work directly with the percent. We always work with the decimal. And then the probability of failure is always 40% or 0.4. Now, this is saying specifically that exactly 2 watches are digital. Exactly 2 watches are digital. All right, now, this next part, okay, again, I'm going to show you how to do this a lot quicker, okay, but I'm going to start off thinking about this. All right, well, the first 2 customers that come in might buy digital, and then the next 4 are going to buy analog. It's a possibility. It might change. It might be the first customer buys digital, the second analog, and then the third customer buys digital. Okay, do you see what I'm getting at here? Okay, the first customer might buy digital, and then the fourth customer might buy digital. Oh man, are you serious, Mr. Ellering? This looks like a lot of work. Okay, well, okay, I do not expect you to have to do all of this. That would be crazy. That would be way too time consuming. So we've got a different way of doing this, okay? How many ways is this going to occur? First of all, okay, how many ways is this going to occur? Well, if you remember, we have things called permutations and combinations. Okay, remember that? Permutations and combinations. A permutation is where order matters. A combination is where order does not matter. Okay, Well, ladies and gentlemen, the customer, we don't care what two customers buy digital. Okay, we don't care what two customers buy digital. We want to know how many ways can the two customers out of the 6, how many ways can that happen? That is a combination, folks. Okay, that is a combination. Now, if you remember, C stands for combination. There are 6, okay, there are 6 customers. 2 of them are going to buy digital. That's going to tell us how many ways this can occur. So if you remember on your calculator, you go under math. Well, first you got to type the 6. Let me start there. Type the 6, go to math, go to probability. It's over on the right side, and it's number 3, combination. And then 2, and you get 15. Now you would have went, well, what about if I would have done the analog? Okay, well, there's 4 people that buy analog, right? So just to show you, ladies and gentlemen, that 2 digital out of 6 is the same. There's the same number of ways with 4 analog. Look at that, huh? All right, 15. So there's 15 ways, ladies and gentlemen, that this can occur. There's 15 ways that this can occur. Okay? Now, I want to show you this notation, because this notation, you're going to see this on the formula chart, which I'll show you in a little bit. The notation that they use for a combination on the formula chart uses parentheses like that, and then the 6 goes on the top, and the 2 or whatever you're going to put is on the bottom. Okay, so that's the notation on the formula chart. Actually, let me pull that in and show that to you right now. Okay, it's this part right here, okay, which you see right there. That's that notation, and you can see this is binomial distribution. That's the notation for the combination, okay? N is the number, fixed number. K is representing the number of successes. Okay, but now how are we going to find, how are we going to find this probability? All right. Well, there's 15 ways that this can occur. So here we go, ladies and gentlemen. We want to know the probability that X equals 2. X is the number of digital, right? The probability that X equals 2. So this is what the notation looks like. Here we go. Equals 6 customers, 2 are digital. That's the combination. Times. Now, the probability of success is 0.6. The probability of failure is 0.4. So this is success, this is failure. But we're not done. How many customers were successful in buying a digital? 2. So the exponent on that 6 is a 2. The exponent on the 4, how many failed to buy a digital? 4. Okay, so that's the setup, and that's what this is saying on the formula chart. Let me go back to that, folks. That's what this is saying. So now you have P to the K. That means the probability of success to how many there were, times 1 minus P, which is failure, to the N minus K, which means how many failed. Okay, so that's what the formula looks like for this. All right, let's go back and set this up. So we're going to take, we already figured out that it's the combination of 6 customers, 2 successful is 15. So 15 times 0.6 squared times 0.4 to the fourth. All right, it's calculator time now. So we're going to go 15 times 0.6, please use parentheses, squared, because that was 2 successes, times 0.4, the failure, to the fourth power. So here we go, folks. The probability of 2 customers coming in and purchasing 2 digital watches is 0.13824. All right. And I'm going to go ahead and I'm going to stop at like 4 digits past. So I'm going to go 0.1382. If you want to go all the way, that's fine. You can do that. So we need to say the probability. I'm going to type this instead of write it. Okay, it's being really slow here. Oh, that's really big. Okay, sorry, folks. Let me fix that. And we don't want yellow. Let's just go with black. So the probability that 2, and if I spell anything wrong, I apologize, 2 customers buy digital watches, ES, is 0.13882. So there is less than a 14% chance. Oh, I need to be more specific than that. The probability that 2 customers, I got to be more specific, out of 6 will buy digital watches is, you have to be very specific. The probability that 2 customers out of 6 will buy digital watches is 0.13. So there is less than a 14% chance 2 of 6 customers buy digital. Okay, it didn't say it to put it in a percent. You don't have to put it into a percent unless it says it, but I just wanted to throw that in there. Okay, so now that was, again, very specific on digital watches. All right, 2 digital out of 6 customers. Okay, this is what I showed you with the combinations. You will find that on page, whoops. You will find this on page 518. Okay, that's the combinations, folks, for binomial. Here's the formula that I already showed you on the formula chart. It's also on page 518. All right, now this one says, what's the probability that no more than 2 watches sold are digital? Ooh, okay, the last one was exactly 2 were sold. All right, this one is no more than 2. Well, how does that change it? Well, that means the probability that X again is representing the number of digital, no more than 2 would be less than or equal to 2. Oh, okay, well, what does that mean? Well, that means it might be 2 watches that are digital, or it might be 1 watch that is digital, or none of the watches were digital. Wow, okay, well, what is this going to look like when we set it up? Well, here we go. So we already did this first one, 6 customers, 2 digital, and then this was 0.6 to the second power, because 2 customers successfully buy digital, 0.4 to the fourth power, okay, plus, now 1 customer is successful, so 1 out of 6, so now this will be 0.6 to the first power, obviously you don't have to put the 1 there, then 0.4 to the 5th power, because 5 of them bought analog, plus, 6 where none of them bought digital times 0.6 to the 0 power times 0.4 to the 6th power. All right, now let's see if I have that answer written down to save a little bit of time here. I do have that one written down. So you could type all of that in. Okay, well, first of all, let me redo this. So this is going to be 15, right? 15 times 0.6 squared times 0.4 to the 4th plus, okay, 6 combination 1. Okay, let's go ahead and look at that. 6 combination 1 is 6. 6 combination 0, ladies and gentlemen, is 1. All right, there's only one way that can happen. So this is going to be 6 times 0.6 to the 1st times 0.4 to the 5th plus 1 times 0.6 to the 0 times 0.4 to the 6th. And to save time, ladies and gentlemen, I already got this figured out. That would be 0.1792. Okay, 0.1792. And then if this was a test, you need to write out a sentence conclusion. So we would say, and I'm not going to take time to do this, I'm just going to say it. So the probability that no more than 2 watches out of 6 sold are digital is 0.1792. So there's less than an 18% chance that 2 or fewer out of 6 customers will buy the digital. All right? All right. Moving on. Now, this one, ladies and gentlemen, okay. What is the probability that more than 3 watches sold are digital? 3 watches. Well, more than 3 watches. More than 3 watches. Okay, well, that would mean the probability of 4 plus the probability of 5 plus the probability of 6, right? Okay, we could do that, folks. Okay, because it's a fixed number, it goes up to 6. However, if you really put some thought into this, the probability of x being greater than 3 can equal the complement of 1 minus the probability that x is less than or equal to 2. Okay, and we figured that out already, didn't we? Or did we? All right. Unfortunately, ladies and gentlemen, that does not include the 3, if you think about it. Okay, greater than 3 is 4, 5, 6. And this setup is actually not going to work. So my apologies on getting you like, hey, yeah, no, it's not going to work. Okay, unfortunately, that will not work because the 3 is not included with that. So just to save time, folks, here's what the setup looks like. Okay, so all right, here we go. So it would be 6, 4, and then it would be 0.6 to the 4th power plus 6, 5. Whoops, hold on here. We have to do 0.4 to the 2nd power plus, now 6 customers, 5 of them buy digital, 0.6 to the 5th times 0.4 to the 1st plus 6 customers, none of them buy digital, times 0.6 to the 6th. Whoop, this is supposed to be 6, sorry. 6 customers, 6 buy digital, times 0.4 to the 0. None of them buy digital, okay? I was ahead of myself there. All right, so again, I apologize for setting that up. You can't do the complement there because the 3 was not included with that first one. All right, just to save time, folks, again, this is 15 times 0.6 to the 4th times 0.4 squared. 6 combination 5, that is 6, times 0.6 to the 5th times 0.4 to the 1st, plus 6 combination 6, ladies and gentlemen, that is a 1. So 1 times 0.6 to the 6th times 0.4 to the 0. Type that in, ladies and gentlemen, and you get 0.54432. All right, and then write a sentence conclusion. Okay, moving on, because this video is already 26 minutes, and that I'm going to save for the second part of the video. Let's look at another example really quick. I want to do 2 more examples. And again, if you like, pause and come back to it later if this is too much all at once. All right, here we go, folks. So here's another situation. A manufacturer produces a large number of toasters. From past experience, the manufacturer knows that approximately 2% are defective. 2% are defective. In a quality control procedure, we randomly select 20 toasters. 20 toasters. We want to determine the probability that no more than one of these toasters is defective. First of all, is this a binomial situation? All right, so conditions. Number 1. All right, success. Okay, success in this case, ladies and gentlemen, that's going to be the defective toaster. Like I mentioned earlier, it doesn't have to be a good thing. So success is a defective toaster. Okay. Failure in this situation is not defective. Okay, because we're specifically looking for defective toasters, so that's going to be our success. All right. Condition number 2, fixed number of trials. Yes, the fixed number of trials is 20. Condition number 3, independence. Okay, each toaster is independent of the other. Think about it. One toaster cannot influence the other toaster being defective. Okay, 4, fixed probability. Of success. Well, the fixed probability of success is 2%, or 0.02. So that means there would be a fixed number for failure, right? 0.98 would be the failure. But you don't have to write about the failure for that one. You can just say for success. Okay, so yes, this is a binomial. This is a binomial probability distribution. All right, let's go to the next question. All right, determine the probability that exactly one of the toasters is defective. So the probability that X is the number of toasters that are defective. Okay, you probably should define that somewhere if this is a problem. Okay, which I didn't do. So, but it does say it in the problem already, so I guess you don't have to define it again. So that is going to equal, okay, ladies and gentlemen, there's 20 toasters. So 20 at the top, one defective toaster. The probability of success is 0.02. There's only one defective toaster. The probability of failure, which in this case is a good thing, is 0.98. And there's 19 of them that failed. But that's a good thing in this situation. Now, if you type that in, ladies and gentlemen, okay, the 20 combination 1 is going to be 20. All right? So there's 20 ways that can happen, times 0.02 to the first power, times 0.98 to the 19th power. All right, to save time, ladies and gentlemen, that is going to be 0.27249. Okay? And then you would write a sentence. The probability that exactly one of the toasters is defective is approximately 0.27. You could round it then, is approximately 0.27. Or the probability that exactly one of the toasters is defective is approximately, well, let me back that up. You could also do it like this. There's approximately a 27% chance that that exactly one of the toasters out of 20, be specific, out of 20 will be defective. Be specific. Okay, moving on. I'm already past 30 minutes. Woo! All right, so define the variable x. Okay, we already did that. That's the number of defective toasters. Now, the mean and the standard deviation. Okay, I didn't show those to you yet. Let's go to the formula chart. Okay, here's the mean, ladies and gentlemen. The mean is simply the how many times the probability. Easy enough. All we have to do is multiply two numbers together. The standard deviation is going to be the square root of the how many times the probability times its complement. Well, that's easy. Okay, the binomial mean and the binomial standard deviation are one of the easiest things to find. You just have to remember how to use your formulas. Okay, so, whoops, I didn't mean to close that again. Got to go back to the other sheet. All right, so this is all we have to do, ladies and gentlemen. So to find the mean, all we need to do is take n times p. Well, it's 20 toasters times 0.02 for success of a defective toaster, and that's 0.4. Yes, it's a decimal. I know you can't have part of a toaster, but that's what it is. That's the mean. That's how many toasters you expect to be defective out of 20. Okay, the standard deviation, ladies and gentlemen, is the square root of the how many times its probability times its complement. Okay, remember 1 minus p is the complement. So all we have to do here is take the square root of 20 times the 0.02. Whoops, that's not a 0. 0.02 times the 0.98. Okay, I'm not going to take time to show that on the calculator, but put that in on the calculator. Please practice it. You should get 0.626. Now, I know it doesn't say it here, but remember, you can't work directly with variances. So if we ever had to do anything more, you can't work directly with standard deviation, sorry. You can back up and find the variance. So to find the variance, remember, all you have to do is take the standard deviation and square it. Okay, but we don't. Just reminding you of that from our last chapter. All right, let's keep going here, folks. Okay, find the probability that at most 2 toasters are defective. So again, that's the probability that x is less than or equal to 2 at most. So what does that mean? Well, that means you could have 2 toasters, or you might have 1 toaster, or you might not have, whoops, trying to write too fast here, write and talk at the same time, or you might have 0 toasters. Okay, so what does that look like? That looks like this. 22 toasters, 0.02 squared times 0.98 to the 18th power plus 21 toaster times 0.02 to the first power times 0.98 to the 19th power plus 20 0 toasters 0.02 to the 0 power times 0.98 to the 20th power. All right, and I'm not going to do the combinations for that, so this is what you end up with, folks, 0.9929. So the probability that at most 2 toasters out of 20 are defective is 0.9929 at most. Okay, at most. All right, that's it for that one. Let's keep rolling here, ladies and gentlemen. All right, do I want to do the deck of... Oh, we want to look at this. Okay, so let's quickly look at this. So if you draw a card from a standard deck of 52 playing cards, observe the card and replace it, the card within the deck, okay, and replace the card within the deck. Count the number of times you draw a card in this manner until you observe a jack. Is this a binomial distribution? A reasonable probability model for this. Okay. This is the key part here. Until you observe a jack. That's not fixed. That's violating rule number 2. So no. Fixed number of trials does not fit. Okay? Again, it has to be a fixed number of trials. All right, I think that was it for that example. Yes, it is. I got one more, and ooh, okay, I've had longer videos than this, so we're doing all right. We're at 37 minutes. Here we go. Thank you for bearing with me here. So, Amarillo Slim, a professional dart player, has an 80% chance of hitting the bullseye on a dartboard with any throw. Suppose he throws 8 darts, one at a time, at the dartboard. Let X equal the number of bullseye. Okay, describe the 4 conditions. All right, ladies and gentlemen, so number 1, okay, I'm going to use S and F, okay, S for success. Now, don't do that on my test, don't do that on the AP test, okay, I'm just abbreviating here. So, success here, ladies and gentlemen, is hit bullseye. Okay, failure, obviously, then would be miss. I'm just going to put miss bullseye, okay, to save time. Number 2, fixed number of trials. I'm just going to put fixed, but you be specific. Fixed, okay, 10 darts. It's right there. 3, independent. Okay, each throw does not influence the other. Okay, 4, success, probability of success. Probability of success, ladies and gentlemen, in this case is always going to be 80% or 0.8. Okay? All right. So, what's the probability? He hits the bullseye exactly 7 times. Again, you would need to define X. Always define your variable. So X here is the number of bullseyes, right? So 7. So that's going to be 10, 7. Success is 0.8, and there were 7 successes. Failure is 0.2, and there were 3 failures. Okay, now the combination for that is, oh, I don't have it down, so I'm not gonna, you can figure it out, folks. Okay, but in the end we get 0.20. Okay, 0.20. So approximately 20% of the time he will get exactly 7 bullseyes out of 10 throws. Again, being very specific. All right, okay, now the next one, find the probability that he hits the bullseye 8 or more times. Okay, 8 or more times. So the probability that x is greater than or equal to 8. So in this situation, that would be 8, 9, 10, because it's fixed. Okay, you set it up, folks. Please set it up and see if you get this answer. You should get approximately 0.678. You set it up, see if you get that. All right, you set it up. All right, this next one. Finally, okay, I hope you're still watching because this one, I really got to emphasize on this one. Find the probability that he hits the bullseye at least 4 times. Okay, the probability of at least 4 means 4 or more. Right? Now, folks, think about this. That would be the probability he hits 4 all the way up to all 10. That's a lot of stuff because you're doing 4 bullseyes, 5 bullseyes, 6 bullseyes, 7, 8, 9, 10. Whoa. Okay. This is not so bad with letter C with 8, 9, and 10. There were only 3 situations there. But here, if you go from 4 to 10, that's 7 things, and that's a lot of stuff to type into the calculator. There is another way you can do these, which I was trying to get to earlier in the video, using a complement. One minus the probability that x is less than or equal to 3. The complement of 4 or more is 3 or less. Okay, the complement of 4 or more is 3 or less. So here we can use the complement rule. So this would be 1 minus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0. You're going, well, that doesn't look like all that much less work. Okay, it is, ladies and gentlemen. Believe me, it is. Okay, it is less work at setting it up. Now, I'm not going to go through and set that up. I'm going to give you the answer, and I want you to see if you can get the right answer. Okay, if you can get the right answer, then you've got this binomial stuff down. You should get 0.999. Okay, you should get 0.999. All right. Find the probability that he hits the bullseye no more than 3 times. Okay, no more than 3. That would be less than or equal to 3. Okay, and again, that would be 3 plus 2 plus 1 plus the 0. Okay, and you would get approximately 0.0009. Okay, see if you can get that. Set it up and see if you can get that. Pause the video and do that. Okay, find the mean. Oops. A little too enthusiastic there. That's just take n times p. So in this case, the mean would be 10 throws, times 0.8. So 8. So the mean, the expected number of times to hit the bullseye out of 10 throws is 8. That is his expected value. All right. How about 20 throws? 20 throws. Okay, well, that would simply be 20 times 0.8. So that's going to be 16. We would expect him to hit 16 bullseyes. Okay, find the variance. Okay, well, the standard deviation is the square root of n times p times 1 minus p, right? That's the formula for the standard deviation. So the variance, ladies and gentlemen, is simply the n times p times 1 minus p. Because if we square it, that cancels out the square root. So the variance here, ladies and gentlemen, is simply going to be 10 times 0.8 times 0.2. And we get 1.6. All right, so again, that's the variance. And with the 20 throws, what's the variance? Okay, the variance is 20 times 0.8 times 0.2. And that's going to give us 3.2. And then if I want to know the standard deviation, I simply take the square root of that. And so the standard deviation would be 1.79. All right. Again, I'm sorry I went over quite a bit. We were up to 47 minutes. Thank you. If there's any part of that you don't understand, please ask in class, and I'll be doing other problems in class also. So hopefully I didn't mess you up when I made a few mistakes in there. All right, thank you.